Hello everyone. I'm inviting everyone for our rubber industry tech talk. Today I'm going to talk about advanced thermal characterization technique of rubber materials. The main focus of this technical talk is more about making all to understand about the advanced thermal characteristic techniques which are available for rubber material characterizations. So we all know how important the thermal characterization techniques for rubber materials and rubber polymeric materials. But at the same time, there are various advanced and unique testing options available today with those standard equipment, which really help us to do a advanced characterization, which give us much more detailed understanding about the rubber materials. So before getting into today's topic, let me quickly give an overview of TA instrument, who we are, what we make. So if you see that today TA instruments, we are basically rooted from a DuPont, which is one of the world-known chemical company originated in 1960s by a group of thermal analysis specialists. They started a special techniques which are very much important for polymeric material characterization. And way back in 1990s, as the demand for the thermal analysis became very popular, and there's more and more requirement for equipments, the company people, the same group of people who was dealing with the thermal analysis, got separated and founded a new company called TA Instruments. And then 1996, Waters Corporation has taken over TA Instruments, and today we are very much part of Waters Corporation. Waters focuses, as you know, they are mainly into HPLC mass specs. TA is mainly into material characterization, especially thermal, rheology, microcalorimetries. Our headquarters is in US. What you are seeing in this campus is our major headquarters, which are located in Newcastle, Delaware State, US. And if you see that we have almost 1,000 employees, and 50% of these employees are directly customer-facing activities, and 13% are involving in R&D. That's where the development of new instrumentation, new measurement techniques are developed. And coming to manufacturing, we have totally 5 manufacturing sites across the world, 4 in US and 1 in Germany. Coming to direct sales and service, we have operation almost 26 countries covering 4 continents, including North America, Europe, Asia, as well as Brazil. Each countries we have a technical sales, application, training support, and training service engineers. So we provide a complete support for our customer, starting from the pre-sales and even after sales. When it comes to application development, training, we are there to support. So what do we make? As you know, TA Instruments, we are having 4 product verticals. One of our major strength is thermal analysis, where we have products like DSC, TGA, STT, DMA, GMA. And coming to rheology and rubber rheology, we have range of equipments which are used for understanding about the rheological properties of both polymer, pharmaceuticals, personal care products, as well as rubber. And third group is mainly for microcalorimetry, where we have a range of products like nano DSC, isothermal titration calorimeter, thermal activity monitors. So these microcalorimetry products are very much mainly for the life science industries, where people who are working on proteins, ligands, those kind of things. And then 4th product groups are about thermophysical properties. Again, here we have got various instruments such as dilatometer, thermal conductivity, diffusivity. These instruments are mainly used to understand the physical properties, thermophysical properties such as thermal expansion, shrinkage, thermal conductivity, diffusivity. With that series of product, we are actually touching every aspect of material. You can name anything. It could be a polymer, thermoplastic, pharmaceuticals, thermoset, inks or coatings, rubber, elastomers. We are there. We have a solution for that. Okay, we have our instruments. And most of our customers are using our equipments mainly for having a better understanding about the molecular structure of your particular materials. And that's what most of our customers are using our kind of equipment. And today also what we are going to focus is more about thermal analysis, where I'm going to show you how our instruments are going to help you to have a better characterization about rubber and rubber polymeric materials. Let's get back to the topics of today's about thermal analysis. When it comes to the typical properties which are measured by thermal analysis, one is the weight. So we subject the sample to basically to the temperature, change in temperature, and then we will be seeing how the weight of a sample is going to change. That is we call as thermogravimetric analysis. Another aspect is about the heat flow. So when you change the samples, when you change the temperature of your sample, how the heat flow is changing. So that is we made it by measuring the heat flow. And that is the two techniques today we are going to focus. One is the weight, how the weight, that is by performing analysis on the thermogravimetric analysis. Another aspect is heat flow. So that give you more information about the thermal transition of the particular polymeric material by using differential scanning calorimetry, or we call it DSC techniques. There are other aspect is length, that is we call it thermal expansion, and modulus, which is by dynamic mechanical analysis, and viscosity, that you can do it by rheological. We have previous tech talks, you can refer those things like how DMA analysis and rheology is going to be helpful in that aspect. So as I said, today we are going to focus more on the weight and heat flow part. So let's start with the TGA, that is what is thermogravimetric analysis. So in thermogravimetric analysis, the main aspect that we are going to measure is change in weight of your sample, or change, it could be of loss or it could be of gain, and against the function of temperature or time under the control atmosphere. So basically the thermogravimetric analysis, or TGA, is going to measure the sample weight changes with respect to temperature or time and a controlled atmosphere. So what are the common use of these equipments? Mainly as far as rubber is concerned, you can perform a composition of the material. Suppose, as all of us know, rubber is a multi-component system. So we have multiple components that if you have a better understanding about the composition of the particular rubber compound, you can make use of a TGA techniques, and that gives the information about the composition of the particular rubber compound. And also it be a very helpful tool to understand the how much of filler, it could be of inorganic filler, how much of filler is there, or if in case of a pipe fiber reinforced plastic, how much of fiber content is present. That information also TGA can give. Another major aspect is carbon content. As all of us know, in rubber industry, carbon black is a very important aspect to improve its mechanical performance, and one has to clearly understand how much of carbon black is present. It could be of a quality control aspect, like if you want to maintain a consistent mixing quality, you can do it. Or if in case of doing something of a benchmark compound or a defective compound, you want to do a comparative studies where you want to understand the carbon black content. And then comes the predict the thermal stability aspect. So this is about the raw polymer. So one has to understand what is the usage temperature of a particular rubber polymer. For that also, TJ would be the good tool to understand the thermal stability. And the third aspect is to characterize a material due to sorption, desorption, or volatile decomposition, oxidation reduction. Suppose in case you are dealing with some sort of a hygroscopic polymeric material which has a tendency to absorb moisture. Obviously, the moisture which is present in the polymer can affect your performance. So the TJ is the techniques that can clearly quantify how much of moisture present in. In case of an unreactive monomer which is present as a solvent, you can also use a TG as a techniques to quantify how much of solvent content inside the samples. So altogether, TJ is the fantastic tool to have a clear understanding about the material composition and how much of filler content into that. So what is critical as far as TJ instrumentation is concerned? The previous slides, what I showed to you is the TA instrument discovery series TGA. So when it comes to any instrumentation, before you purchase any TGA equipment, there are a couple of key aspects that you need to see. One is the furnace. The furnace is the one which controls the heating rate. Furnace is the place where you control the heating rate as well as temperature. You maintain a particular temperature, and then you can also see the atmospheric control. So the furnace is one of the very important aspects. And then comes change in measured temperature that is being measured by basically a thermocouple. And the third, of course, is the balance. Here, the balance is the heart of the system, any TGA, because that's the one which is going to measure the change in weight, actually. So these are the three major criteria. So when before any selection of TGA, you need to see how the furnace is going to control, the heating temperature and the temperature and thermocouples, how it is accurately measured the temperature. So you need to see how much of temperature accuracy and resolution, and then comes the balance performance. Let's talk about more about the key application what TGAs can do. As I said at the beginning, I explained to you the major application is about thermal stability of a material. That is the one of the key aspects, and that is something in terms of predicting the lifetime of your product. So suppose you have the polymeric material, a rubber polymer. How are we going to predict what will be the lifetime of the particular polymer? That thermal aspect, because many occasions the material can be subject to thermal and mechanical loading condition in a real world condition. But here the TJ can give you the information about, if respect to temperature, how stable it's going to be your material. Another third aspect is oxidative stability of material. The polymer can be exposed to condition at elevated temperature where there is a higher chance that oxygen can attack the polymeric material, and there could be a chance of degradation. So TGA can help you to evaluate that aspect also. And comes to third is the composition of multi-component system. And the same things, this will actually, what we do is, as the polymeric materials, rubber polymers consist of many components. As you know, it consists of high volatile component, and then we have the plasticizer, and then we have those polymeric component, and then filler, oils. All those things are mixed together. As we heat the sample, samples start going to evaluate one by one, and that also will be coupled with the evolved gas analysis techniques. In this case, we couple the TGA with the either FTAR or mass spec, and that also give the information further that what type of evolved gas is coming out. This will also give a clear understanding about what type of decomposition byproduct which is evolving from the sample, and many times it also helps us to identify the polymers. Okay, so if you want to have a better understanding about what is coming out of sample, you can make use of TGA with the evolved gas analysis. Okay, and then as I told you, the TGA, we have the option to change the atmosphere. Most often studies would be performed at nitrogen atmosphere, but sometimes you can also do in a reactive atmosphere, and then you can see how the material is going to decompose in particular atmospheric condition. Apart from that, we have moisture and volatile content of the material, estimation of lifetime of the product, and also we can understand the decomposition kinetics of the material. So these are some of the key application, and here I'm going to highlight some of the TGA application in a tire rubber. For example, here you can see this is a typical standard TGA thermogram where you can see we have taken an 11 mg of tire compound and analyzed in the ramping mode. So we are taking a few mg of sample. Generally, it will take 10 to 20 mg of samples and put it at a crucible, TGA crucible. It could be made up of either platinum or ceramic, and then we heat it up the ramp temperature of 20 degrees centigrade per minute up to 600 degree under inert atmosphere, where in this case it's nitrogen as the inert gas. So what we observe is, you can see on the x-axis is basically a temperature, and y-axis we can see on the left hand side is a weight percentage, and then y-axis y2, which is on the right hand side, what you see is the derivative weight. So as we heat the samples, we start from the 100% and the sample has start decomposing. As you can see, at a lower temperature, we can see the high temperature volatile oil components start coming out, which accounts to 6.12% of weight changes. As we heat further, okay, we see the polymer decomposition, which is account to almost 51.84%. Okay, at this point, the weight is again getting stabilized. At this point, once the temperature reaches at 600 degree, that's when we do a gas switching. So we switch from nitrogen to air, which further burn up the carbon black which is present in the polymer compound, and then immediately we can see the weight changes of correspond to the carbon black decomposition, which account to 38.96 in this particular case. And finally, what we see is the residue and the ash content, which due to the presence of filler content, which is of 3.031%. So now you can see from this analysis, we can clearly define the composition of the polymeric material. And what you can see here is, what is so peculiar here is that as you see the polymer decomposition, the derivatives show the kind of a solder, which signifies that which is not a single polymer decomposition, it may be a multiple composition. So the many occasions, since we are using a multi-component system and mix of polymer blend, standard TGA would be a kind of a challenging aspect. And here another aspect is the atmosphere what we are using. As we all of us know, the decomposition of any polymeric material, whether it's rubber polymer or thermoplastic, is basically a kinetic reaction, and that is purely dependent on the atmosphere what we are using. In this case, we have taken the same rubber compound, tested under air condition and tested in nitrogen condition. So what we see here is there is a clear change. The sample which is tested in air is basically okay, it is basically of showing a faster decomposition as compared to the nitrogen atmosphere. So which clearly show this particular graph, even though the rubber chemistry is same, the atmosphere has a major effect which has totally changed the decomposition kinetics. So what this signifies that, so the furnace control is something is very, very important, and that's where we need to be very careful in selecting the TGA, how well the TGA, the furnace is going to control the atmospheric, whatever the atmospheric control. And also the task switching is also to be very fast and efficient. So that is this particular analysis to show how well the atmospheric condition of either air or nitrogen is going to have an impact on the decomposition kinetics. Now let's talk about the limitation of standard TGA, and then we can talk about the advanced mode what is there, it can be a solution for dealing with this kind of complicated situation. Many times, if you look at the standard TGA, you may see a kind of a complex thermal scan with broad weight losses, like what you see here. And many times you see overlapping weight losses with multiple peaks and shoulders. Like you can see here, the sample is showing a multiple decomposition pattern, and also it is kind of a overlapping. So when you do the composition analysis, actually you should know the onset of decomposition, end set, so that you can easily calculate the associated weight loss. But in this case, since the transitions are overlapping, it is a bit difficult for you to easily calculate when exactly the decomposition is starting. Okay, and many times, many occasions, we may have this kind of challenges when you're running that TGA samples. So here comes the advanced mode called IRS TGA, which is basically a sample control TGA. So one should understand the difference between a temperature control TGA and sample control TGA. In sample control TGA, okay, what we are doing is we are regulating the heating rate based on the decomposition of nature of your sample. If you look at the left hand side, here we define the heating rate. So irrespective of sample decomposition or the weight changes, the TJ is going to ramp up the temperature in the predefined heating rate. Whereas on a sample control TJ, as you can see on the right hand side, your sample weight loss also is a part of your control algorithm. So what happens is, the beginning of the run, the sample will be heated at a faster heating rate. As soon as the TGA senses there is a sample weight changes, it will easily slow down the heating rate and allow that particular decomposition to complete. This way it will have a dynamic heating rate. So depending on the pattern of how the sample is going to decompose, the control mechanism or the associated heating rate also is going to change, and that we call it dynamic heating rate, high resolution TG. So what is the improvement you are getting? You are able to resolve those decomposition pattern in a better way. So that's one of the key advantage of the decomposition pattern. So that is what you see here, how the decomposition pattern is resolved in a better manner. And your derivative peaks looks be very sharp, and that is the advantage of your high resolution TGA. Here we can see the kind of example for the polyurethane samples. Just for the information, you can see we taken a polyurethane. If you see the decomposition, which is the standard heating orange color curve, the standard heating rate is running by 10 degrees centigrade per minute. The high resolution TGA is starting at 50 degrees centigrade per minute. Okay, so what we see is that very sharper peak, and you can see the clear shift of your decomposition pattern. But look at the derivative peaks. Now the derivative peaks clearly show a sharp peaks. So now we can able to get those decomposition pattern in a much better resolution, and we can also clearly separate those overlapping events. This is the clear advantage of a high-res TG. Like now, I could show you a simple EBDM rubber car high-res TGA part. So this is again what you can see here. The green curve is a conventional TGA where you'll be heating at a standard ramp rate of 20 degrees centigrade per minute. Coming to the blue curve, which is high-res TGA, like what you can see is here. Now you can see the blue curve. The derivative peaks looks very sharp, and that is because of a better resolution. So in this case, though we started off the heating rate initially at 50 degrees centigrade per minute, as soon as the sample reaches the initial weight losses, which is being absorbed around 420 degrees centigrade, okay, the heating rate will be completely reduced, which allow the sample the kinetics to complete, and we allow totally the sample to decompose, particularly that, and that will give a sharper weight losses. Afterwards, again, once the weight getting stabilized, your derivative is coming to close to zero, the heating rate kicks off again and going to the higher range. Finally, we go to the next level of decomposition. This way, we are resolving the overlapping things, and that also will help us to quantify each weight losses in a better manner, and that which could be of complicated in many of the standard DSC run. And this is the clear advantage of the high-res TJ. Another high-res TJ option we have is a high-pressure TJ. Pre-estimate is giving this high-pressure TJ as model called HPTJ 750. If you see that in a normal TJ run, we always study the material property in two aspects. One is either time and temperature, or we will be changing the atmosphere. But we all know that the kinetics of decomposition also varies with respect to pressure. But pressure is often an ignored aspect. And if you come to the real world condition, the polymeric materials or rubber materials, whether during the processing time, it might be subject to elevated pressure. You can just imagine of extruding the rubber hose, where the rubber polymer material definitely would be exposed to the higher pressure, extrusion pressure. And we may not have the idea how a particular rubber polymer is going to behave at that elevated temperature and the pressure. And that's where that high pressure TJ is going to give you. This is offered by TH, an advanced technique, a patented techniques, where we are using some unique technology called, magnetic suspension balance, which also facilitate not only do the studies at elevated pressure, also you can use some corrosive atmosphere. You have a pre-gas mixing solution that will connect it to pre-reactive system, gas system, and you can create a very corrosive atmosphere, which is many times not possible on the standard DJ. So this is one of the very superior technology. The benefit what you are getting is that you have a better idea how the particular polymeric material is going to decompose under the higher, not only as a function of temperature, at the same time as a function of pressure. Here I can show you the studies what we have done on the PVC materials. So the blue one is actually performed at the pressure of 1.2 bar. The heating rate is 10 Kelvin per minute. So it's a standard heating rate. And you can see clearly the two step changes of a PVC. One is first it will evolving the axial from the things, and then second decomposition is correspond to the loss of aliphatic and aromatic hydrocarbons. Now, same studies we are doing at an elevator pressure which is at 80 bar. So what we see here is you can see clearly though the onset of reaction at the same temperature, but the studies which we have done at the 80 bar shows the faster decomposition rate as compared to the studies that we performed at the lower pressure. So this clearly signifies how pressure is actually, fasten up the decomposition process, and that is the idea we can do. So by using these techniques like high pressure TJ, you have an ability to study the material behavior not only with respect to temperature or time, but also as a function of pressure, which give us a much more deeper understanding of material, and that will help you, in fact, to design your processing when it comes to dealing with a particular polymer, and that will help you to avoid, lot of situations during processing of your particular polymeric material. Another is about the decomposition kinetics. So if you want to understand how the decomposition kinetics is happened for a particular rubber materials, basically this is the ASTM techniques. Pretty much all the DJ can do that. The principle is fly and wall techniques, where we would be doing the study at a different heating rate. And as I told you, the decomposition is the kinetics, so it's always depending on the heating rate and the time. So if you are doing at a slower heating rate, the material will decompose at the lower temperature. At a faster heating rate, you can see clearly the decomposition will shift to the higher temperature, and that is because of the kinetics what is involved. And what we do is basically we capture the conversion rate, which is basically as the ASTM technique, at 3 to 4, 6 different heating rates, and then we plot the heating rates versus inverse of temperature. The slope is basically giving the activation divided by the the gas constant. That multiplied by the gas constant will give you the activation energy. So if you wish to understand how is the activation energy of your decomposition, basically you would be doing this faster studies actually. Okay, but now you don't need to do this kind of study. The benefit of it is we have a techniques called modulated TGA. I'm skipping this because this is basically, the idea is how you can do this study, understanding of polymer kinetics, decomposition kinetics by single run. As I explained, the normal ASTM techniques which involve multiple heating cycle, but whereas in this case we don't want to perform multiple. In a single heating cycle, you would be able to calculate the activation energy. So that is called modulated TGA. The way it would work is that instead of applying a standard heating rate, we would be applying a modulated temperature ramp. So in a sinusoidal fashion, then there is a backdoor algorithm which will plot the activation energy, like in this current thermogram. What you see is a polytetrafluoroethylene. So we can see a simple state changes, and then we plotted the activation energy at the real time. As the sample undergo the decomposition, we can see how the conversion head present, what is 354, the activation energy of that particular samples. So that's about the advanced techniques on the TGA. Let's talk quickly about the DSC part. So what is DSC would be doing? So DSC is basically a differential scanning calorimeter. It will measure the how much of heat is being changes with respect to the temperature of your samples. So we put the sample and reference, and then we heat it subject to heating, and then we can see how the sample is undergoing the changes, especially when it undergoes any phase transition. It could be of glass sunshine temperature, crystallization, and melting. So that we can measure the associated heat flow of that. So let's say if you see the heat flux DSC, there are two concepts are there. One is heat flux DSC, power compensation DSC. Heat flux DSC as offered by TH have many better advantages as compared to the not power compensation DSC. In a heat flux DSC, you have a same furnace, single furnace. In fact, you have a reference sensor, sample sensor. You keep a few milligram samples on the crimped pans on the sample sensor actually. Okay, and then we will see that how the sample of your temperature of the sample is changing with respect to temperature. So the fundamental equation is two. The heat flow changes would happen due to two aspects. One is heat capacity changes and kinetics. The heat capacity changes is usually basically, for example, as the sample undergoes the glass function temperature. So what is happening is your heat capacity is going to changes before and after the glass function temperature. So that the TGA, the DSC can detect as a heat flow changes. When, for example, a sample is undergoes some changes with respect to kinetics. For example, we can, let's say you have a rubber compound which undergoes some curing process, that can be measured by kinetics as a function of temperature. That also is going to alter the heat flow. So this will give the complete information how the sample is going to change its transition or the associated kinetic transition, and we can able to quantify the heat associated with that particular transition. So that's about the Discovery DSC 25,000. So what you can see here is like if you look at the typical thermograms, so we classify that whenever sample undergo any endothermic or exothermic activities, we can see that as a shift in the heat flow. So in this case, when the sample undergoes glass constant temperature, which is absorbed as the endothermic freeze, like if in case of crystallization, the curve is going to the exothermic direction. So we see a exothermic freeze, and then if it's a melting, you can see a endothermic peak. Same way, if you are dealing with something like a thermosetting, let's say like a polymer rubber compound, which is undergoing some curing process, then you can measure the cross-linking by measuring the exothermic reaction. Okay, and further anything in sort of oxidation, you can measure from the oxidation part. Like in case if you wish to say OIT application. Now I can see how DSC is helpful to understand the percentage of cure. Here I presented two curves, so you can see the solid green line curve, which is of optimal cure condition. So how do you understand whether the polymer is completely cured or not, or under cured? You can use a DSC as a technique to determine this aspect. So there are two ways you can see. One is by looking at the glass constant temperature of a cured material. When you look at the green compound, okay, clearly the glass constant is showing at minus 5.27 and the exotherm is showing about 79.3. So what you need to do is you first take the sample, uncured sample, run the DSC, allow the sample to 100% cure, and that measure quantify how much of energy which is required. In this case, for particular DSC samples, we need a 320 joules per gram of energy is required. But what we see here is the optimum Q is 79.3. So if you take the ratio, we can clearly calculate that the green color sample is 75% Q. Whereas the blue compound, which is so even the lower TG as well as higher residual Q. Okay, so this is the second time we are keeping the sample on the DSC, where in the second time we are seeing this thermograms behavior. So coming back to the blue curve, when you account the energy which is higher 145.4, if you take the ratio, the blue color compound is basically it's queued only 55%. So that is the reason we say that the sample is underqueued, and that also reflects your glass transfer which is at the lower temperature. So this way you can see how the DSE is really helpful to understand things. So now I want to talk about the advanced mode about MDSC techniques. MDSC is the one of the pioneer and most advanced techniques in DSC. The major benefit here in MDSC is that it will first of all it will increase your sensitivity of detecting a very weak transition. And second major advantage is that it also helps us to evolve that overlapping thermal transition. Just imagine many times you would be running a sample of mix of polymer. It could be a mix of two polymer, and you are trying to understand the glass transition temperature of two polymer, which might be occurring at a close temperature range, which is many times difficult to understand. But doing MDSC, you can able to resolve those things in a much better way. In MDSC, what we are doing is, again, just like modulated TGA, in modulated DSC, we instead of applying a linear ramp, we apply the oscillatory temperature ramp at a fixed amplitude and the period. So in this particular case, you can see if you take a small portion of the the heating ramp, you can see a sinusoidal temperature ramp with the variation of plus or minus 0.42 degrees centigrade and period of 40 seconds. And overall ramp we are maintaining at 4 degrees and up to the temperature of 290 degrees centigrade. And this way, what's happening is modulated DSC signal will give three signals. What is total heat flow, which is as similar like a normal heat flow, what you get for the standard heating rate. But apart from that, you get three more heat flow signals. What is reversible heat flow? That is the blue curve, and then the non-reversible heat flow, which is the brown curve. So if you closely look at the thermogram of each individual heat flow signals, you can see the heat flow, the green one, carry all the information. Like for example, in this case, we can see clearly the step changes followed by cold crystallization and then melting. When you look at the reversible heat flow, which is basically only showing the transition which are reversible or thermodynamic in nature. What is glass transition temperature, melting point. So these are the thermodynamic spot which is being easily measurable. Another is the the non-reversible, which is shows all the kinetics event. Even you can see a small endothermic peak which is occurring close to the glass transition, which is because of a enthalpic recovery, and then followed by the crystallization and then crystal perfection. So this way, now you are better equipped to detect where exactly the glass transition temperature is, and the glass transition temperature also looks very broader and very detectable manner. So that's what we are talking about here. The MDSC can give you three signals total, which carry all the transition. The reversible heat flow, which is only going to show the heat flow which are related to heat capacity, and non-reversible, which are going to take all the transition which are due to the kinetics, could be of evaporation, crystallization, curing, all sort of that sort of transition. Now I'm going to show you, this is my last application. I'm going to show you how a practical situation the moderated DSC is going to be helpful. Many times polybutadiene, which is one of the important rubber compound which is being used in entire industries, and we generally mix that polymer with other polymer. Okay, so it would be sometimes very difficult to quantify how much of polybutadiene is present in a particular mixture. So the DSC can be used for that purpose. When you run the 100% butadiene, what we see here in this, we can clearly see a glass function temperature which is around -100. So in DSC, you have an ability to take it to the negative temperature. In this particular DSC, the DSC run is performed with the help of liquid nitrogen. So we started off from -160 degrees centigrade, and then we can see a clear step changes because this is 100% polybutadiene. So we can able to see that. And then again, as you heat further, the amorphous compound convert to crystallize. And as you heat further, you can see the endotherm, which is due to the welding. And same is reflecting in the heat capacity signal also. You can see the heat capacity is increasing above the glass transition temperature. Now, when you come to the low content polybutadiene, because this is the unknown samples, but we want to understand how much of polybutadiene is present in this particular polymer. When you look at that, it is very difficult, nearly impossible to detect those glass transition temperature which correspond to the polybutadiene. Now, what we are doing is the same samples we've been testing in modulator DSC. Okay, and now you have the ability to clearly plot the reversible heat flow because as per our experimental condition, we need to see the reversible heat flow, which is going to show the transition of especially the glass function temperature of the polybutadiene in that. So we are plotting here the reversible heat flow against reversible CP, also against the temperature. And what we see, we could clearly see the step changes, and also we quantify how much of heat capacity changes. If you go back to my previous slide, so in this slide, if I hope you are all able to see this slide. So if you see the step changes is well pronounced, and we can see clearly that. And what we are getting is the range of 0.336 joules per gram. And this is the total heat capacity of 100% polybutadiene. When it comes to now, we are measuring a 0.022 joules per gram degree centigrade. If I take this average, okay, I can clearly quantify even a 6.6% polybutadiene, which is present in the polymer, accurately by using modulated DSC. So this is one of the key advanced benefit of this, modulated DSC techniques, and that is what you are getting out of this analysis. With that note, I summarize my presentation. As I highlighted, TA Instruments is today one of the recognized market leader in advanced thermal analysis equipment. We have a large selection of thermal analysis products and techniques available for a thorough material characterization, and we catering to broad application area, whether it is polymer, pharmaceuticals, life science, energy. We are offering a comprehensive solution for a thermal analysis, your thermal analysis problems. And we also committed to innovate the new technology. So that's what we are talking about. Some of the techniques like MDSC and all those techniques. Okay. With that note, I'll summarize my presentation. I thanks for these wonderful opportunities, and I would be happy to have any questions if you have. Thank you. Over to Parag.